Ladies and gentlemen, welcome to hopefully the last lecture from chapter number 6 from the Eigenvalues and Eigenvectors chapter. Well, I will continue today with what we started in lecture 15. So this will be lecture 16. And hopefully, even though I will go a little bit over time, I will be able to cover everything that I want. Well, we'll continue with finding the eigenvalues and eigenvectors for matrices. We'll consider a 3x3 matrix, and then we'll also consider the eigenvalue problems for linear transformations. And in the second part of the lecture, we will talk about the diagonalization of matrices. But to get to that, we need to talk about the eigenvalues for similar matrices. In other words, I will also require some knowledge, which was given in lecture 14 when we talked about similar matrices, when two matrices are similar and so on. So, okay, let's get started. And I remember last time we start talking about the eigenvalues and eigenvectors of a matrix. And the last example that I had that we did was to find the eigenvalues of for this 3x3 matrix. So this was okay. So this was the example, right? To find the eigenvalues and the eigenvectors of this 3x3 matrix. So, so far we found only eigenvalues and eigenvectors for 2x2 matrices, but now we'll see how to find these for 3x3 matrices. Okay, now keep in mind that I want to go back to the general strategy for finding the eigenvalues. I just want to remind you this general strategy of finding eigenvalues and eigenvectors. And if I have, so this general strategy is the following. If I have a n by n matrix, n rows and columns, then the first step is just to form the characteristic equation, which is basically just setting up the polynomial, the characteristic polynomial to 0, the characteristic polynomial of degree n. Since I have a n by n matrix, the characteristic polynomial would be of degree n is given by this PA of lambda, which is the determinant of lambda times the identity minus the matrix A is 0. All right. So this is step 1. Step 2 is to find the real roots of the characteristic equation, which is this right here, this box, this equation in red, the determinant of lambda I minus A equals 0. And once we find out the, so this roots will be nothing other than just the eigenvalues of the matrix A. And step 3, for each eigenvalue, we need to find the eigenvectors, the corresponding eigenvectors. And by solving the following homogeneous system, which is given by this, right? Lambda I, so we take each eigenvalue and we solve this system. As you can see, the first one, lambda I times the identity. So lambdas are, the eigenvalues are scalars times the identity, minus A, well, this will be a matrix, then X will be a vector, and this I'll have here the 0 vector. So I have to solve this system of equation. And this will require row reducing an n by n matrix. And now, once we obtain that reduced row echelon form, then the reduced row echelon form that must have at least one row of zeros. Okay. Okay, with this in mind, let's find the eigenvalues and eigenvectors for this 3x3 matrix. And also I'll ask another question as well. Maybe let me ask a supplementary question, why not? What is the dimension of the eigenspace of each eigenvalue? we also want to add this supplementary question. As you can see, the problem is pretty straightforward, right? Okay. All right, so like I said, step one is just to write the characteristic polynomial. So the characteristic polynomial of A is given by, and let's write it, PA of lambda, which we said that this is the determinant of lambda times the identity minus A, or sometimes we just denote it by this, lambda times the identity minus A. And this is nothing else, so let's write it. This will be, so the matrix A is 2, 1, 0. So this is lambda minus 2, negative 1, 0. Will be the determinant of this. 0, lambda minus 2, 0. And the last one, so 0, 0, lambda minus 2. And now, once we compute this determinant, surprisingly, well, it's kind of easy to see what is the value of this. And I'll leave it to you as an exercise to figure it out. It's lambda minus 2 cubed. So that will be the determinant. Well, as you can see, this matrix is triangular, so you can say something about the determinant of triangular matrices, and we have seen that like a long time ago in chapter 3. Okay, now let's see this equation. It's obvious that it has degree 3. But the only solution to this equation, the only solution of this equation is given by lambda equals 2. Well, I would say something about the multiplicity, but I would do it as a remark afterwards. And now we need to find, so to find the eigenvectors of the eigenvalue lambda, so this is the eigenvalue. To find the eigenvectors of lambda equals 2, we need to solve the homogeneous linear system, so it will be lambda I minus A, which in our case lambda will be 2I minus A, and multiplied by the vector x equals the 0 vector, right? Okay, now let's see. We see that 2I minus A, 2 times the identity minus matrix A, is nothing else than just, let's write 1, 0, 0, 0, 1, 0, 0, 0, 1, minus 2 times the matrix A. The matrix A was 2, 1, 0, 0, 2, 1, 0, 0, 0, 2, no, sorry, 0, 2, 0, and the last one was 0, 0, 2. Okay, and this computation here will simply give us, if we do the computations, this will be sorry, I made a mistake here. It's 2 right here. It's 2 times the identity, not the identity minus 2. Anyway, so this will be 0, negative 1, 0, 0, 0, 0, 0, 0, 0. Okay. Well, this implies that that what? That if we set up the parameters, let's say x1 to be an s, or x3 to be a t, with s and t real numbers. So once we solve the system, you solve the system, it's quite clear what the solutions are. Just look at it. If we said then, and x2 will be 0. So we can conclude that the eigenvectors of the eigenvalue lambda equals 2 are of the following form, and now let's write them. So this will be, my vector x will be x1, x2, x3, and we know who x1 is, and so on. So this will be s0t, or if you want to write them, this will be s times 1, 0, 0 plus t times 0, 0, 1 with s and t real numbers. And not both 0. This is important. So we can say that the eigenvalue lambda equals 2 has two linearly independent eigenvectors. So now we can answer also the question. So the dimension of its eigenspace, guess what? Since I have two linearly independent eigenvectors, so the dimension of its eigenspace is clearly, as you can guess, is 2. And that's it. End of story. Right? So this is how we determine the eigenvalues and the eigenvectors of a 3x3 matrix. As you can see, the story is quite similar to 2x2 matrices. It's basically the same. All right. Okay. Now, let's point out the remark here, because in this example, you have seen that I only had one eigenvalue, but the degree of my characteristic polynomial was 3. And I want to point out the following. If an eigenvalue, let's say lambda I, occurs as a let's say a multiple root, and let's just say that this root it occurs at k times of the characteristic polynomial, okay, right? Then we say that that lambda I, this eigenvalue, has multiplicity k. That's what we say. This guy has multiplicity k. Well, I can say even more. This implies that that lambda minus lambda I to the power k, right, is a factor of the characteristic polynomial and lambda minus lambda I to the power k plus 1, right? So the next one is not a factor of the characteristic polynomial. Right? Well, as we have seen in this previous example, the eigenvalue lambda equals 2, if we look back again, you see, was the root of this characteristic polynomial lambda minus 2 cubed, everything cubed. In this case, we can say that lambda equals 2 has multiplicity 3, is of multiplicity 3. And the dimension of the eigenspace of the eigenvalue lambda equals 2 is 2. All right. In general, I want to remark here one more thing. In general, the multiplicity of an eigenvalue is greater or equal than the dimension of its eigenspace. This is important. Anyway, there are two types of multiplicity, the algebraic multiplicity, the geometric multiplicity. I'm not going to go into that. So far, what you need to know is that there exists this multiplicity. An eigenvalue can have multiplicity 1, 2, 3, and so on, depending on what is the degree of its characteristic polynomial. Now let's go even a bit further and have this another example. Example number, I'm not good with numbers. This was 4. Now let's see number 5. Example number 5. Again, we want to find the eigenvalues of, and this time I'm going to pick 5 by 5 matrix. Oh my goodness. Let me see. 5 by 5. Okay. So I already done this example, so I don't want to redo it. Just pick any matrix on the, wait, a 4 by 4, not a 5 by 5. What am I talking about? 1, 0, 0, 0, 0, 1, 5, negative 10, 1, 0, 2, 0, and 1, 0, 0, and 3. Okay. Okay, so let's find the eigenvalues of this matrix. You can see I have 4 rows, 4 columns, a 4 by 4 matrix. That's pretty brutal, but anyway, let's do it. Again, we apply the same method, and we write a characteristic polynomial. The characteristic polynomial of A is given by PA of lambda is the determinant lambda times identity minus A. Okay, now let's write it. So it's lambda times this guy, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, minus the matrix A. Let's write it again. So this would be 1, 0, 0, 0, 1, 5, negative 10, 1, 0, 2, 0, and 1, 0, 0, 3. Okay, and now we do the operations here, and this will be, in fact, this is the determinant of this. I should have said here. Anyway, let me put the determinant here, right? Keep in mind the notation for this is nothing other than just the determinant of whatever, let's say A. So keep this notation in mind, right? Okay, and this will be the determinant of the following matrix. Let's see, lambda minus 1, 0, 0, 0. This will be 0, lambda minus 1, negative 5, 10, negative 1, 0, lambda minus 2, 0, negative 1, 0, 0, and lambda minus 3. Okay, and now the determinant of this, it's a 4 by 4 matrix, and I'll leave it to you as an exercise to figure it out if I've done it correctly. I think I computed it here. So let's see. I think it was something like this: lambda 1 minus 1 squared, lambda minus 2, lambda minus 3. Yeah. Okay. All right. So this is the determinant of this. And now the characteristic equation. Well, it's given by is P A of lambda equals 0. In our case, which is this guy here, P A of lambda is lambda minus 1 squared times lambda minus 2 times lambda minus 3, and we set this equal to 0. All right. The eigenvalues, it's quite clear that when we set this equal to 0, then we obtain the eigenvalues. The eigenvalues are lambda 1 equals 1, lambda 2 equals 2, and lambda 3 equals 3. But you see, this is a degree 4 polynomial, and I have only 3 roots. but one of them is a double root, and in other words, one of them will have multiplicity 2. And let's point this out. Lambda 1 equals 2 has multiplicity 2. And now we need to find a basis for the eigens. Now we find a basis for the eigenspace of lambda 1 equals 1. Okay, for this, what do we need to do? Well, it's 1 times, this is lambda 1, so it's 1 times the identity minus a, which will give us, if we do the computations, okay, this is quite easy. Okay, identity, okay, it's just okay, so this will give us 0, 0, 0, 0. Okay. 0, 0, negative 5, 10. And then we'll have negative 1, 0, negative 1, 0. And the last one will be negative 1, 0, 0, negative 2. Okay. So this is my matrix. The identity minus, and by elementary row operations, this will be equivalent. So I'll leave to you again as an exercise. Anyway, it's very easy to see that we can write this in row echelon form. So we'll leave it to you here, elementary row operations. This matrix will be equivalent with the following matrix in row echelon form. Let me write it here. And that's very easy to see. Well, I have 1, 0, 0, 2, 0, 0, 1, negative 2, and then this will be zeros. Now it's quite clear to see when we look at the system of linear equations. We have 4 variables. Only 2 equations matter here, so it's quite clear that it will have infinitely many solutions. And now we setting x2 to be s and x4 to be t, with s and t real numbers, right? We have the following solution. X to be, now let me write it like this, x1, x2, x3, x4. This will be 0s minus 2t. Let me write it in this way. s plus 0 times t, 0 times s plus 2 times t, 0 times s plus t. And this will be, and if we factor, we see that this is s times 0, 1, 0, 0. Plus t times negative 2, 0, 2, and 1. Okay. So a basis for the eigenspace corresponding to lambda 1 equals 1 is given by this. Let's write this B1, this basis, corresponding to, so it will be given by what? By this vector 0, 1, 0, 0, and negative 2, 0, 2, 1, right? The ones that you see here. And now, so this is a basis for lambda 1 equals 1. Let's keep that in mind. And now we have to do the same thing basically for the other eigenvalues. And I already did this, since I don't want to lose too much time with it. I'll just tell you directly, and I'll leave it to you as an exercise. Similarly, the eigenvalues lambda 2 equals 2 and lambda 3 equals 3 will produce, so using the same procedure, will produce the following eigenspace basis. Right? And according to my computations, these are given by, so B2 is, let me see. Well, it's only 1. 0, 5, 1, 0. Okay. So this is a basis for lambda 2 equals 2. Okay, that's beautiful. And now we also have that B3, another basis, B3 is given by, again, only one vector. It's 0, negative 5, 0, 1. Okay. And that's a basis for lambda 3 equals 3. Okay. Well, as you can see, this was a 4x4 matrix. We kind of went a little bit off the grid here. It's pretty involved, so I just I didn't do all the computations. I just cut some of them. I just told you. Well, I've done them before this lecture, so that it wasn't necessary for me to lose any more time to compute also the eigenspaces for the other two eigenvalues, to solve systems of linear equations and so on. Anyway, if I do one, I think the others should be pretty similar. So I'll leave this to you as an exercise to figure this out. Okay. As you can see, this is what happened for 4x4 matrices. We can find the eigenvalues using the same procedure. But now, what if we have a 5x5 matrix or 6x6 and so on? Well, finding eigenvalues for matrices of order n with n greater or equal than 4, even with 4, can be very tedious, right? So it's kind of, I wouldn't say it's the fastest way of computing the eigenvalues, but that is the way to compute this, right? Well, there are also some numerical, it's worth to mention that there are numerical methods of approximating eigenvalues. When we have, let's say, I don't know, a 10 by 10 matrix, and we want to compute the eigenvalues, there are this so-called numerical methods in linear algebra which approximate these eigenvalues. Anyway, I'm not going to go into that. This is much more math involved here, and I think a numerical analysis course will give you much more insight about this. Okay, so this is how we find the eigenvalues of matrices. We have seen a 2 by 2, 3 by 3, now a 4 by 4. And now I want to mention something in particular, some special matrices, because I'm going to deal with this type of matrices in the future. Well, we have seen something about triangular matrices, and I want to address this question. What are the eigenvalues of triangular matrices? Right? And this, we will answer this question with the following theorem. I don't know the number anyway. Well, if A is an n by n matrix, then its eigenvalues are the entries on its main diagonal. It's that simple. Keep that in mind. So the entries of the main diagonal wait, what? I forgot to say the magic word here. Oh my. If I leave it the way like this, that's not even true. I forgot one word here is an n by n. Okay. N by n triangular matrix. That's the word I forgot, triangular matrix. Then its eigenvalues are the entries on its main diagonal. Is that simple? Let me give you some examples. Quick examples. And the first example I have in mind, let's say, so find the eigenvalues of each matrix. And let me pick a 3 by 3 matrix. Let's say pick a triangular matrix. Let's say 2, 0, 0, negative 1, 1, 0, and now 5, 3, negative 3. Okay. For this matrix, if you look at if you identify the main diagonal here, look at it. Right? These are the eigenvalues. And now let's see another example. Let's say we'll consider this matrix B, and now let me take a big one. Let's say negative 1, 0, 0, 0, 0. Okay, so it's a 5 by 5. This is a 3 by 3. This is a 5 by 5. What? And now let's 0, 2, 0, 0, 0. And then let's see, 0, 0, 0, 0, 0, 0, 0, 0, let's say -4, 0, and now the last one 0, 0, 0, 0, and 3. And let's identify the main diagonal here. Look at it. Are these elements right here? Right? Well, it's quite clear if you want to do the classic way, but I'm just gonna, well, if you would like to compute the determinant of this, well, and I'll leave it to you as an exercise, but I can tell you based on the previous theorem. So you can do like this. You just set up the characteristic polynomial to be equal to 0, which is the determinant of lambda I minus a. Anyway, I'll leave it to you. You set it equal to 0, and then you find the eigenvalues. But I can tell you directly that the eigenvalues, and then you will find, so I'll leave it to you as an exercise, and you will find that lambda 1, let's look, is 2, lambda 2 is 1, and lambda 3 is -3, right? These are the eigenvalues, which are elements on the main diagonal. The same story for goes for B. Goes for B. Well, P of B lambda is nothing else than just a determinant. This time it will be a 5 by 5, lambda times the identity minus B. And again, I'll leave it to you as an exercise to do it the hard way, but I'm just going to tell you that the eigenvalues, we will find that lambda 1 will be, let's look at the -1. Lambda 2 will be 2. Lambda 3, so it's a 5 by 5, I'll have 5 of them. Lambda 3 will be 0. Lambda 4 will be -4. And lambda 5 will be, again, 3. Wait, again? No. I have -1. Oh, my. -1. Yes, -1, 2, 0, -4, and 3. Well, this is how it's very easy to find the eigenvalues. And every time when you have a triangular matrix, you know exactly what are the eigenvalues. And that's a very, very important thing, because we want to use this kind of reasoning when we deal with diagonalization of matrices. Okay, I think this wraps up the story for finding the eigenvalues and eigenvectors for n by n matrices. Well, we have seen it in the example of 2 by 2, a 3 by 3, even a 4 by 4. Now I gave you an example even of a 5 by 5. Fortunately, it was just a triangular matrix. And now the other thing that I would like to discuss here, which will be related with the previous chapter, when we talked about linear transformations, is what are the eigenvalues and eigenvectors of a linear transformation? So we want to see this, how to study the eigenvalue problem for a linear transformation. So let me address this question. What are the eigenvalues and eigenvectors of a linear transformation. That is the question we want to answer, right? Well, let me just, okay. Well, the story began with the eigenvalue problem for a matrix, right? Given a matrix A, we wanted to find out which are those numbers, which are those matrices for which AX is lambda times X. Well, the same thing will go here, since we can associate a matrix to any linear transformation. Eigenvalues and eigenvectors can also be defined in terms of a linear transformation. Okay. So eigenvalues and eigenvectors can also be defined in terms of a linear transformation. Right? Let's say T, which goes from the vector space V to V. In other words, we say the following: a number, okay, let's call this definition. A number lambda, right, is an eigenvalue of a linear transformation, let's say T from V to V. Okay, when there is a non-zero vector X, right? Just like such that, just like in the case of the matrices, we have that such that T of X is lambda X. This non-zero vector, the vector X, the non-zero vector X, is called the eigenvector. It's called an eigen. It's called give me 1 minute. This vector X is called an eigenvector. Of T, corresponding to the eigenvalue lambda. Okay. Moreover, the set of all eigenvectors of lambda okay, with the zero vector included. This is important. Is nothing other than just the eigenspace of lambda. Is the eigenspace of lambda. Okay. And now let's see, well, I would like to see just an example, and I think probably we'll stop here and I'll do another lecture talk probably separately about the diagonalization. So this is the eigenspace of the lambda. And now let's consider where is the, ouch, sorry about that. Okay. Let's consider the following linear transformation. Let's take one from R3 to R3, whose matrix relative to the standard basis is the following. Let's say, let's pick a 3 by 3, and let's just say is 1 3 0 3 1 0 0 0 negative 2. I think we have, and the standard basis. Let me remind you that standard basis for vectors in R3 is given by the following. So it's B. It will consist of these vectors 1 0 0 0 1 0 and 0 0 1. This is standard basis. And I think we have seen this example. I didn't, yeah, I think we have seen this example in the previous session in I think in lecture 14. One can find that that the matrix okay, that the matrix of T relative to the basis, let's say B prime, and I think the basis was 1 1 0, 1 negative 1 and 0, and the last one was 0 0 1, right? Is the diagonal matrix, right? Is the diagonal matrix, and remember it was that A prime which was found in such way that there existed an invertible matrix P such that A prime is P inverse times A times P. And according to my computations, that A prime is nothing other than just 4 0 0 0 negative 2 0 0 0 and negative 2. And the non-standard basis was this one here, right? Let me write it again. So the non-standard basis was given by this. B prime is 1, 1, 0, 1, negative 1, 0, and 0, 0, 1. Right? That was the non-standard basis. You can see it here. Okay. Now, I want to do one more example, and I think this should be enough for this lecture. And probably I'll go further with another lecture discussing the diagonalization of a matrix. And example, I don't know the number, I forgot. Find the eigenvalues and a basis for each corresponding eigenspace of the following matrix. And again, I'm going to take a 3 by 3 matrix. Let's do it. 1, 3, 0, 3, 1, 0, 0, 0, negative 2. Okay, I'm going to take the same matrix. I think we've taken this matrix again. Well, I just modified it a bit. Well, the characteristic polynomial, of A is given by PA lambda is the determinant of lambda times the identity minus the matrix A, or you can write it like this, or this is nothing else than just, and now let's see, 1, 2, 3, lambda minus 1, negative 3, 0, negative 3, lambda minus 1, 0, 0, 0, lambda plus 2. We need to find the determinant of this guy, and the determinant of this guy will be oh my. Okay, let's see. So the determinant of this guy, probably it will be, okay, lambda minus 4 times lambda plus 2 squared. Okay. The characteristic equation, so we get the following, we obtain the following eigenvalues. And I'll leave it to you as an exercise here to compute this. We obtain the following eigenvalues. Lambda 1 will be 4, and lambda 2 will be negative 2. And as you can see here, lambda 2 equals negative 2 has multiplicity 2. Right? We have seen that. And now clearly, basis for the eigenspaces are B1, 1, 1, 0, right? And B2 will be, well, it's will be some 1, negative 1, 0, and let me see. I think I've done them here. Okay. So 1, negative 1, 0, right? And 0, 0, 1. And you can verify this. So I'll leave them to you as an exercise. So exercise to verify this. Anyway, and that's it. And now I want to make a comment on this result. want to point out some things, some remarks. This example, as you can see it, right, illustrates two results. The first one is that if, let's say, if I have a linear transformation T from R3 to R3, is the linear transformation whose standard matrix A, whose standard matrix is A, and wait, let me try A. Okay, and let's say B prime is a basis for R3 made up, okay, well, that's a term, made up of the three linearly independent eigenvectors. I hope what I'm saying makes sense. Wait. Okay. Okay, independent eigenvectors corresponding to the eigenvalues of A, then the matrix A prime, then the matrix A prime for T relative to the basis, and that was the point. So the basis B prime, guess what, is diagonal. That's exactly what I wanted to reach at. And let's keep in mind that also the main diagonal diagonal entries of the matrix A prime are the eigenvalues of A, are the eigenvalues of A. Now let's see, let's look at this matrix. In fact, no. So this was, A was 4. So, okay, A prime that we obtained was, I think, let me look at my computations. This was, okay, 4, 0, 0. 0, -2, 0, and 0, 0, negative 2. Okay. Okay. So as you can see here, I have the eigenvalues. These guys here. So these are the eigenvalues. Of my matrix A. And the non-standard basis is B prime was what? Ouch, sorry about that. 1, 1, 0, 1, negative 1, 0, and 0, 0, 1. Well, we will see this, how we're going to develop this. As you can see, this is a diagonal matrix, A prime. And in the next section, lecture, we'll discuss these results in great detail. So that's why I'm a little bit vague right now. Okay, guys, I think I'm going to stop here. There will be another video, and probably that's it. We will end up with eigenvalues and eigenvectors. Thank you very much.